Hello, it's me again. Now, we have to start at the beginning of everything. And what was that? Well, that's what's called the Big Bang, not the show. And basically, it was just like a single point in space, and it just exploded and expanded, and created everything really. Um, and it's the universe is still expanding from there, and actually that's how one of the ways it's hypothesized to end. The big rip, everything gets ripped apart as it stretches. Don't worry, you'll be dead. Now, what exactly formed in the Big Bang? Well, it was just like a lot of hydrogen and helium, and so those are the two most abundant elements in the universe still. And like, when did this occur exactly? It's uh, through things like redshift measuring and cosmic background radiation. We've determined that this occurred like 13.8 billion years ago, and we don't really know what was before that. Before the Big Bang. I don't know, Big Chungus. I don't know. Now, galaxies. Pretty cool. You live in one. Now, what is exactly a galaxy? Well, it's a collection of like dust and gas and billions of stars held together by gravity. And now there are three different types. Now there's the elliptical, spiral, and irregular. You may have, by those names, figured that you live in the spiral kind of galaxy, the Milky Way. There are usually supermassive black holes in the center. There's one in ours. Now, let's talk about nebulas. What are those? Well, it's like a giant cloud of dust and gas in space. Now, there are three ways that a nebula can form. First one, supernova. As it explodes, everything goes everywhere. We'll start again, the process. Now, to form a reflection, emission, and dark nebulas, it comes from the gravitational interaction between just, gases in space. So they just come together over time, and gravity takes over, and they become, together. Now, a planetary nebula are when the star reaches its final stage and starts expelling outer layers. And now, what elements were present in our nebula as our solar system formed? It was mainly a lot of hydrogen and helium. You'll find that's a recurring pattern. And so, what eventually causes a nebula to collapse? Well, as I said before, gravity takes over and puts these things together. But over time, it gets there's enough gravity because there's enough mass that it collapses. Now you may ask, okay, as it collapses, it starts spinning, right? Okay, what direction? Well, it spins counterclockwise. You may ask why. I don't know. But the spinning causes the material around the center of the condensing, collapsing nebula to flatten out. So starts spinning and flattens out the stuff as it rotates. Now this brings us to a solar system forming. Yeah. Now the collapsing nebula, what starts spinning? Protostar. Now what's that? It's just a very early star, very young. What causes it to start fusion and become a main sequence star? Well, that's when there's it condenses enough, there's enough pressure that it starts smashing helium or hydrogen into other hydrogens, forms helium, massive energy. That's when it gets around 10 million Kelvin inside. So once it gets enough pressure, enough heat, it starts fusing. That's what makes it a main sequence star. Now, it's around this time that protoplanets start forming. Protoplanets are just built through the collisions of planetesimals, masses that just orbit in about 100 million years. They actually start to enough collisions, not enough to hit anymore. They start forming terrestrial planets. like the ones found in our solar system. Now, speaking of terrestrial planets, what exactly makes how a star and planet different? Well, it's important to note that they both have layers, so they're similar in that regard, and they both have a very hot core. Most of them. Ours has a very hot core. Mars, not so much anymore. But stars are really different. For one, their size. Stars are usually massive compared to any planet. And stars emit light, while planets, not really. They just orbit and reflect the light. Well, speaking of stars, how do we classify them? Well, there's a type of diagram called an HR diagram, also known as a Hertzsprung-Russell diagram. I'm just kidding, nobody says that. It shows the relationship between a star's temperature and its luminosity. And it's very useful in showing, like, the, I guess, life cycle of a star. And on the x-axis, we have the temperature, which reads in order from hottest to least hot: O, B, A, F, G, K, and M. And then the numbers on the y-axis are for the magnitude of how bright it is, its luminosity. Now, an HR diagram shows the 4 groups of stars, being the main sequence, giants, supergiants, and white dwarfs. Now, what does each fuse in its core? Well, white dwarfs, they don't do anything. Now, main sequence is when it takes the hydrogen to helium, and as they get to the giant and supergiant phase, they run out of hydrogen and they start fusing helium into carbon and carbon to neon and so forth in the chain, as you can see, until they get to iron, which can't be fused anymore because it's pretty tough. Why do you think we make stuff out of it in Minecraft? You know what I mean? So yes, our star is a main sequence star, and it will be that way for a while, like 6 billion years, until it becomes a red giant and swallow up the inner planets. That'll kind of suck. Don't worry, you'll be dead. Now, let's continue speaking on stars. Let's talk about supermassive stars. Now, massive stars are can be classified as stars with like more than 8 solar masses, or SMUs. Their main sequence stage, they fuse hydrogen to helium, and in their giant phase, they do the rest of the kebab, as said before. Now, how did they die, and like what is formed when they do? Well, for one, the more massive a star is, the faster it burns through its fuel supply, so the quicker it dies. And so most massive stars can burn out and explode in a supernova in like a few million years. Except for like hydrogen and some helium created after the Big Bang, as said before, all the stuff around us and our Earth and all these dense elements were created in stars. Now, as stated before, the mass of a star plays an important role in its life, also plays an important role in its death. Now, if a massive star's mass is like less than 40 SMUs, it usually becomes like a neutron star. But if it's greater, it gets a little spicy. It can become a black hole. Well, we talked about massive stars. Let's talk about low mass stars. They are usually consistent between 0.61 SMU to less than 8. And they fuse hydrogen to helium, main sequence star, but then they can go on to form helium to carbon, as they get older and do the rest of the chain again, and they become red giants. And when they get closer to dying, they expel their outer layers because they can't hold on to like them anymore, right? And so that's one of the ways planetary nebula, remember, can be formed, as these outer layers shed. And so what's left over is just the core. And that is what a white dwarf is, just the core of one of these kind of stars. Now, what's the internal structure of a kind of star like this? Well, we can look here and we can see, the core, the convective zone, the radiative zone, the corona, and then, sunspots and sun flares, and of course solar wind, that's always getting blown out at us. Thank you, Sun. Alright, but most familiar to you, probably a terrestrial planet. I assume you're on one. Now, how close do terrestrial planets usually orbit a star? Closer than most others. And this is because when a star starts fusing, pushes out, or, solar wind and stuff like that, pushes out. And the denser stuff, it's harder to push back, but the lighter stuff can go further away. So, as planetesimals start forming, remember, they can, it's usually the denser stuff that's around this area, so that's what the planets, terrestrial planets, composed of. Well, what's like the kind of basic composition and structure of a terrestrial planet? Well, so you can see here, usually like a metallic core, solid, because that's where the denser materials are, and then we have like a rocky mantle, and then a rocky crust. And so, when we talk about terrestrial planets and, their distance from a star, it usually comes up with the Goldilocks zone. What's that? Well, it's a special distance from a star, where it's enough, it's the right temperature, just right, for liquid water to be. So it's not too cold, not too hot. So Earth is in this place, and as we look to other solar systems and other planets, called exoplanets, that are in this habitable zone of their star, that's where we like to look for life. Maybe we'll find it. Or you might be dead. But, of course, talking about terrestrial planets, we also have to talk about the Jovian planets. Now, where are they? Well, they're usually further out. Like I said before, the lighter stuff usually got pushed further out than the denser stuff. However, it's important to note that this is not always the case. And there are times where a gas giant migrates inward to the star. It's known as planetary migration. Jupiter would have done the same if Saturn didn't step up. Mr. MVP done his job well. Thank you, Saturn. Now, what are gas giants made of? Their composition? Well, they're largely made of hydrogen, helium. Go figure. But they have metallic cores as, the denser materials. And because of how big they are and the gravitational pressures that they exert on these gases, they actually start to act more like liquids and metals. So we find layers, as we can see here, of like metallic hydrogen, liquid hydrogen, and the outermost layers of like an atmosphere of hydrogen. Now, Jovian planets are also composed of the ice giants, and they're similar to their gas giant counterparts, being composed of hydrogen and helium and some methane in their atmosphere, metallic cores too. But the mantles have water, ice, and ammonia and methane ices. So you can see here. And Neptune is kind of the same as Uranus. Now, as we talk about all these planets, we have to make a little reference to an old planet of ours, Pluto. To be a planet, you need 4 things. And you need to orbit a star, you need to have enough mass to be mostly a sphere, you need to not be a moon, and you need to have cleared your orbital path. Pluto failed that last one, so it got demoted to dwarf planet. See ya. But it will always live in our hearts. Get it? It has like a heart on it. Speaking of not being a planet, the moon. Now, how did it form? Well, there are 5 hypotheses for how it formed. There's only one good one though, don't worry about the other one. It's called the Giant Impact Hypothesis. What does that even mean? It's in the name, bro. So, it means that there was a collision between the Earth early on and a pretty sizable object, maybe the size of Mars, impacted. And this made this happen, where it like reformed and created the moon out of the outer elements, so the lighter stuff. So the moon is a little bit different in composition, but pretty similar. Now this other planet-sized object that collided with early Earth is known as Theia. I don't really know why, but I do know that it occurred around 4.5 billion years ago. So pretty early into the formation of the planet and the solar system. Now, the moon has phases because of its distance from the Earth and how it's tidally lost. Now, what are these phases? Well, in order, it goes new moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, third quarter, and waning crescent. The cycle repeats once a month. You may have heard that the moon causes tides. What are those? Well, tides are just long waves that move across the ocean. Be for real. And it's true. The gravitational forces exerted on Earth by the moon, and to a lesser extent the sun, actually create these kind of tides. Now, what are the that word? What are those cycles? Well, the cycle are the motions of Earth that affect its climate. This includes its eccentricity, which is just how ovally the orbit is, and because Earth doesn't orbit exactly in a circle, because it doesn't orbit the sun, it orbits the center of mass in the solar system, which is a little bit off-put from the sun because of Jupiter. Always ruining things, right? And it's important to note that it oscillates between more elliptical and less elliptical over a cycle of about like 100,000 years. Now, another part of this all is called precession, and that's because of like the little wobble in because the Earth is like slightly off center. Interesting top. Final aspect of this all is called obliquity, and that's the tilt of the Earth, and this is around 23.5 degrees. Now, it's hypothesized that this tilt was caused by the impact with the object that formed the moon. Now, what does obliquity cause exactly, though? Well, it's the reason for the seasons. Now, bringing to a close, we talk about the space race. It was a competition between the Cold War rivals of the US and the Soviet Union to achieve basically superior spaceflight capabilities. And why were they doing this? Well, because of the prospect of like control, and it would send a message to everyone internationally, being like, "Hey, I'm really cool." Now, the first object that was launched into space was on October 4th, 1957, by the Soviet Union, and it was Sputnik 1. What did it do? Like nothing. Just like really didn't do anything. Well, it was kind of like it had no scientific instruments. It was just like it transmitted radio signals back to Earth. Kind of burned up like a couple months later, but started the space race. And on April 12th, 1961, the Soviet Union sent the first man into space. A Soviet cosmonaut by the name of Yuri. Now, the US didn't really like that. We were like, that was cute. We can do it better. So, on July 20th, 1961, the astronauts Neil Armstrong and Edwin Buzz Aldrin became the first humans ever to step foot on the moon. Pretty cool. I'm not jealous or anything. Now, some technologies that are pretty prevalent in society today, thanks to advancements made for space exploration, can be seen as solar panels, or memory foam for your shoes, and artificial limbs. Now, Mr. Lin, I know you're watching. You remember when you said some people will get some extra credit or whatever if we talked about like why those crazy Russians dug that really deep hole for whatever reason and why they did that? Well, I got news for you. The actual purpose of drilling all the way down was to investigate and learn about the Earth's crust, and they found like a transition from igneous granite like above to metamorphic granite below, and this showed that the continental crust is composed entirely of like granite, whereas the oceanic crust is basaltic, and this discovery, it actually helps support the theory of tectonic plates, and that ties in to what we have been learning in class. So I signed that off. I hope this isn't late or anything, because it's probably going to take a while to edit, and the compiling of this video will be crazy long. So I'm recording audio on like a mini phone. Like, do you see this?